Hi everyone, welcome to our webinar this week. This is my pleasure to introduce Rubén Campoy from the University of Valencia. So prior to Valencia, he got his bachelor degree in mathematics from the University of Alicante in 2013, and then master in mathematical engineering from Carlos III, University of Madrid in 2015. And then he got his PhD in applied mathematics from the University of Murcia. Then he did his postdoc in the University of Alicante and then University of Massachusetts, Lowell. And now he's a assistant professor at the University of Valencia. So welcome, Rubén, to Australia again. So now the stage is yours.
Okay, thank you for the introduction, and thanks all the other organizers for inviting me to this seminar. So I'm going to talk about a product space reformulation with in a reduced dimensional space. So this is the outline of the talk. I will start with an introduction to projection and splitting algorithms, and then we'll move to the main section about product space reformulations. I will mention the standard approach, and then we will show the new reformulation, and finally some numerical experiment to compare both approaches. Okay, so in our framework, we work in Hilbert spaces, and we denote weak convergence by this half arrow and strong convergence by the full arrow. So we consider a collection of sets, and we want to find a point in the intersection, which is called the feasibility problem. We might deal with problems with whose intersection is really hard to deal with directly, but instead we know how to compute projections onto the individual sets. So in those situations, we will make use of the so-called projection algorithms. So just to refresh what's the projection mapping, we need a closed and a closed non-empty set, and then the projector is the mapping which assigns those points. So for a given point x, it assigns those points in the sets which are closest to the point x. And then we will use also the reflector, which is 2 times the projector minus the identity. It's just the symmetric point with respect to the projection. And it's in the convex case, the projector is single valued, and also the reflector. So the classical projection algorithms, we start with the alternating projections method. It was originally proposed by von Neumann in 1933 for 2 subspaces. And its iteration is just what its name indicates. It's just project alternating in the sets. So we start projecting onto A, onto B, and so on. So we converge to a point in the intersection. The result was generalized for an arbitrary number of subspaces, not necessarily 2, in 1962 by Hilbert. And finally, the algorithm still works for arbitrary convex sets in the same scheme. So it was done in 1965 by Breckman. On the other hand, and we will be focused more on this second algorithm, Douglas-Rachford, which was originally proposed. The name comes from the paper by Douglas and Rachford. They proposed the algorithm for a particular linear system of equations, but it's actually Lyons and Mercier who provide the convergence theory for the case of feasibility problems for general convex sets, or even in a more general setting of monotone inclusions. This algorithm for given 2 sets, we need to define the Douglas-Rachford operator as the identity plus the composition of the 2 reflectors over 2. And just the fixed point iteration is the DR algorithm. So if we have these 2 sets, and this is the current iteration, we just need to reflect onto the first set, reflect, and take the middle point. Or more generally, instead of having 1/2 of the identity plus 1/2 of the reflectors, any lambda convex combination, everything works. So this is why it's also called the average alternating reflections method, because of this geometrical interpretation. If we have two closed and convex sets and we run the algorithm, the theory says that if the sets, the intersection of the sets is non-empty, then the sequence is weakly convergent to a fixed point. But we need to project this point onto the first set in order to get a solution of the problem. So for example, in this picture, we run the algorithm here, we converge to the fixed point. This point doesn't solve the problem, but if we project it onto the set A, then we get the solution of the feasibility problem. So the sequence of interest is actually the one of the projections, which is known the shadow sequence. And also, this is not a direct consequence of the original convergence. It can be proved that the shadow sequence still converge to a solution. And in the case when the problem is non-consistent, then the sequence is unbounded. Okay, so let's move to the context of splitting algorithms. The framework is exactly the same, but now we want to find a zero in the sum of two maximally monotone operators, where a monotone operator is a mapping satisfying this inequality for every pair of points in the graph. And maximality means that we cannot extend the graph of this operator by the graph of another monotone operator. So maximality in terms of inclusion of the graph. So classical examples of maximally monotone operators recover the subdifferential of a proper lower semi-continuous and convex function. And in this case, a monotone inclusion of two subdifferentials would be not exactly equivalent, but under a CQ, we have the equivalency of a minimization problem. We want to minimize the sum of two convex functions. And another example is the normal cone to a closed and convex sets. In this case, the monotone inclusion will recover the feasibility problem. So feasibility problem can be considered particular instances of monotone inclusions. So for the monotone inclusion, we can also use Douglas-Rachford, and the iteration is defined exactly with the same expression, but now instead of projections onto the set, we have this J gamma A and J gamma B. So this is the resolvent of the operator, which is defined as the inverse of the identity plus gamma times of the operator. And 2 times the resolvent minus the identity will be called the reflected resolvent, which will play the role of the reflector in the feasibility problems. So if we apply Daggers-Rachford, the splitting algorithm for minimization and feasibility problem, we need to consider, in the first case, subdifferential, and the resolvent of the subdifferential becomes the proximity mapping given by this expression. In the case of normal cones, then the resolvent becomes the projector. So this is why we can recover the feasibility problem as a particular instance of the splitting algorithm. So the convergence theorem for Douglas-Rachford in the general case of monotone operators is exactly the same. We run the algorithm, and then this will be, as long as there exists at least one solution to the problem, the sequence will be weakly convergent to a fixed point, but we need to compute the first resolvent of the fixed point in order to get a solution of the monotone inclusion. So again, the sequence of interest is the shadow sequence that it can be proved that it's also weakly convergent to the zero. So in general, not only Douglas-Rachford, splitting algorithms are those methods that can be used to solve the monotone inclusion by taking advantage of the decomposition. So that means that at each iteration, the operators A and B are activated independently, either by a direct evaluation, which is called a forward step, or via the resolvent, which will be called a backward step. So Douglas-Rachford would be a splitting algorithm that only use backward steps. But there are many other splitting algorithms, such as forward-backward or ADMM, that in this case it uses one forward step, one backward step. ADMM is for composition with linear mapping, and there are many others. But we will be focusing on Douglas-Rachford in this talk. So what happens if instead of having only two operators here in the monotone inclusion, we have more than two, say R operators? We still want to find a splitting algorithm in the sense that each operator is activated only once and separately. So what happened in this case? Let's study first the case of feasibility problem. Because when I was talking about projection algorithms, which are splitting algorithms for feasibility problems, in the case of alternating projection, I said that it can be used for an arbitrary number of convex sets. You just project, 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 and so on. But the problem with Douglas-Rachford is that I only define the operator for two convex sets. So when we have, like, say, three sets, the first initial approach would be to include a third reflector here. And even that the iteration generated by this operator is still weakly convergent to a fixed point, now the fixed point might not be useful for solving the problem. Here we have a counterexample. We have three sets, three subspaces here. If we start, for example, from this initial point, we reflect. Now the middle point will be exactly the same. So this is a fixed point of the operator, but this is not a solution to the feasibility problem. And neither if we project into the first set or the third set or the second set, we might not reach, or we cannot reach, the intersection of the sets. So this approach doesn't work for feasibility problem. So this is why we need to use product or reformulations in the product space. So let's see what's the classical standard approach by Pierre. Suppose that we have R sets and that we want to find a point in intersection. Then we need to work in the Hilbert space HR, which is R copies of the space. In this space, in this product space, we define two sets. The first one is the product of the original sets, and the second one is DR, is the diagonal. It contains those points in the product space with all the components equal. And this is equivalent in the sense that X is in the intersection of the original sets if and only if R copies of X is in the intersection of these two new sets. So this is an equivalent two-set problem. Consider, for example, this instance. We want to find a point in intersection of three intervals in R. So these are the three intervals. We're interested in finding points in these black segments. And we want to use, say, Douglas-Rachford. Then we need to consider the product space reformulation, which needs three copies, because we have three sets, three copies of the space. So R3. In each dimension, we need to consider one of the sets, and then we build the product of the sets. So this is our set C, C1 times C2 times C3. And the other set for the problem would be the diagonal, is this subspace here. So in these two sets feasibility problem, we can find the intersection, is this black segment here. And if we project onto its dimension, this coincides, this recovers the intersection of the original sets. Okay, this is the segment in the first set, which is the intersection. So we have the equivalence of the problems, but in order to use projection algorithms, we need to compute projections onto the two new sets. As long as we know how to compute projections onto the original ones, then the projector onto C is can be computed component-wise. So at each component, we project onto each of the sets. And this subspace, so we can find the projection. In this case, we just need to average all the points, and this is repeated in all the components. So for example, in this particular instance, if we want to project this point onto C1 times C2 times C3, we just need to consider it's the composition on the original spaces. This is first component, second component, and third component of this point. In the original space, we compute a projection onto the set. So we project each component onto its set, and then we build the product again. So this new point will be the projection onto the hypercube. In the case of the diagonal, we just need to apply the formula, and we reach the projection. This is a subspace. We just project onto the diagonal. So now we are able to apply Douglas-Rachford in this equivalent problem. This product reformulation, it's usually credited to Pierra and to this paper from 1984. But the case is that there are earlier papers where the authors independently employ the technique. And I would like to thank here the Professor Alex Kruger, who pointed out these two references. This is a paper by 1980 and 1981, where they use the product space formulation. But then I also saw that Spingarn, in his paper about the method of partial inverses from 1983, he also uses the product space reformulation. So we were a bit like confused about what's the original origin of the reformulation, and thanks to Heinz Bauske, he pointed out that actually the reformulation by Pierra was proposed in his thesis, which date is 1976. Okay, so this is why we call it the Pierra's product space reformulation. Okay, so this is the reformulation for feasibility problems. It can be extended to general monotone inclusions. The approach is the same. We have, we want to find a zero in the sum of R maximally monotone operators. So we just consider the product operator A, which is computed component-wise. And this is a maximally monotone operator whose resolvent can be computed component-wise. And now the other set in the feasibility problem case was the diagonal of the product space. Now, if we move to monotone operators, we consider the normal cone to the diagonal. This is a maximally monotone operator whose resolvent becomes the projection. The projector to the diagonal, it's just computing the average of the points and repeat this component, this quantity in all the components. So this JR here is the canonical embedding. That means that given a point in the original space, we just copy it R times. So we build a point in the diagonal. And the equivalence is that the set of zeros of the sum of the two new operators, the product operator plus the normal cone to the diagonal, can be identified as R copies of the set of zeros of the original monotone inclusion. So in the case of Douglas-Rachford, for more than two operators, we need to implement it in the product space with the normal cone to the diagonal and the product operator A. That means, first thing that it means is that we don't need only a point, an initial point, but an initial vector of points. So we need R initial points. So this is our x0 here in the product space. And now for the iteration, first step is computing this resolvent. This is the projection onto the diagonal. So we compute it. Now we consider reflection, and this reflection, it's computed in here, in the resolvent of the product operator. But we saw that this is computed component-wise. So we just, for all I from 1 to R, we compute the reflection, compute the resolvent of the operator, and store it. And finally, the 2 times ji minus I and the lambda convex combination, all the remaining steps, can be summarized in this X update. And then the shadow sequence, which in this case is PK, is the sequence evaluated at the first resolvent. Then it converges quickly to a 0 of the sum. So how does it look like for feasibility problem? So consider 3 sets now. We need to consider first 3 initial points. And for the iteration, first step is projection onto the diagonal. So this is the average of the 3 points. And now for each point, this is this loop, we need to compute first reflection with respect to the P0, reflection with respect to the set, and middle point. And this is the X update. We repeat with respect to the X2 and define the new step, and the same for X3. So reflection, reflection, middle point. So we restart the iteration and we compute P1 as the average of the 3 new points. So if we repeat the procedure, then we will generate this sequence of P's that will be weakly convergent to a point in the intersection. Okay, so have a look at this part here. This is a loop. That means that our algorithm is parallel. We can compute these steps independently. But the problem is that we need to store all the R sequences in order to compute the next step in the iteration. In order to compute the next PK, we need to compute store R sequences. This is what is called recently the R4 lifting of the algorithm. It's like in which dimension lives our algorithm. So for this is the implementation in the product space. With R operators, we need R4 lifting. So now we discuss about what's the minimal lifting for Douglas-Rachford. If we think about the monotone inclusion described by 2 operators, if we implement the VR on the product space, then we get 2-fold lifting because we have 2 operators. But in this case, in the original problem, we can implement the algorithm. In this case, we have no lifting. We can implement it in the original space. Or 1-fold lifting, this is the same. And this must be the minimal lifting. In the case of 3 operators, if we implement VR on the product space, we get 3-fold lifting. So the question was, is that the minimal lifting for VR? So the case is that it was tackled by Ryu in this 2020 paper. And in here, Ryu showed that it is impossible to have 1-fold lifting. So it is impossible to define a Douglas-Rachford algorithm for 3 operators in the original space. We need to move to a higher space. But the minimal lifting is not 3, but only 2. So we can remove one of those sequences in the parallelization of the algorithm. And this was achieved because Ryu provided a new Douglas-Rachford type algorithm with only 2-fold lifting. So the question is like, can we generalize this result for a family of R operators? So We know that on the product space reformulation, the listing is R4. But the question is that minimal, or we can generalize the result and get minimal listing of R minus 1? So this was a question in this, in the work I'm presenting, I showed that the minimal listing was at most R minus 1. But the fact is that now this is solved thanks to the paper by Matt Tam and Yuri Malitsky, where they provided a new implementation of the algorithm in with R minus 1 for listing, and they proved that this is the minimal listing. We cannot reduce it a bit more. So how do we achieve this bound? So by providing a new reformulation in the product space that doesn't use R for listing, but we remove one of the spaces in the product space. So let's see how we do that. This is the standard product space reformulation. We consider the product operator and the normal contour to the diagonal. So in here, what we do is to remove one of the operators from here and merge it with the diagonal. So now in the original product, we have only R minus 1 operators. So here I consider R minus 1 copies of the remaining operators, the R. And in order to make this sum consistent, this is not the normal contour to the diagonal in the space HR, but in the space HR minus 1. So this will be the two new operators defining the reformulation. I'm going to call this P and this is K. And these live in the product Hilbert space H to the power of R minus 1. So we have reduced by 1 this dimension. The case of the main result in this paper is that, of course, B is maximally monotone and we can compute the resolvent component-wise, because this is just a particular instance of the previous reformulation. So the problematic operator is K. K is the sum of two other operators. Let's call this S of X, and this is the normal contour to the diagonal. So we know from the previous formulation that this, as a product operator, is maximally monotone. The normal contour to the diagonal is maximally monotone. But in general, the sum of maximally monotone operator is not maximally monotone. It's only monotone. But the maximality does not hold in general. But for the particular structure of these two operators, we can prove that this is maximally monotone. And also, we want to be able to compute the resolvent of K. The resolvent of K as a resolvent of a sum of maximally monotone operators. In general, there's no closed form expression for the resolvent of the sum. But of course, again, for the same reason, for the particular structure of these two mappings, this is actually the composition of the two resolvents. So we first compute the resolvent of the normal contour to the diagonal, and from here, the resolvent of S. So the first one is the projection onto the diagonal. This is present here. And now, from here, we compute the resolvent of S. But S is the product of AR. So we compute the resolvent of AR. And we embed this quantity into the diagonal. And finally, we need the equivalency of the formulations. Again, the set of zeros of B plus K can be identified with the set of zeros of the original sum. So how does it translate for the case of feasibility problems? Now we need to work on the space HR minus 1. And in here we define two operators. The first operator, set, the first set B, is the product of the first R minus 1 sets. And K is R minus 1 copies of the other set, CR, intersected with the diagonal. And the equivalency is the same as before. A point is in the intersection of the sets if and only if it's embedding into the diagonal is in the intersection of the two new sets. And projections are computed as in the previous slide. Projection onto B component-wise. Projection onto K is the composition of the projection onto the diagonal composed with the projector onto the set CR in all the components. So if we go back to our example, in the new reformulation, we don't need 3 copies of the space R, but only 2. So this is in R2. In here, we consider C1 and C2, only the 2 first sets, and we build the product of the sets. This is our set B in the formulation. And now, in order to build K, we consider the remaining set C3 in both components, and we consider C3 times C3. We also need the diagonal, and the intersection between the diagonal and this product, say this segment, is K. So we again have an equivalent feasibility problem, because in the intersection between this box and this segment, which is the black segment here, if we project onto the individual dimensions, we get the intersection. This is exactly equivalent. The problem is, of course, computing the projection onto the new K. In the case of the set B, the projector is computed component-wise, as we did here. In the set of the projector onto K, say, for example, we want to project this point onto the blue segment. This is computed by composition. So we first project onto the diagonal, and from here we project onto the square, C3 times C3, which can be done component-wise. And this is the projection onto K. The key fact here that makes this composition to be the projection onto K is that when we first project onto the diagonal, so once we are in the diagonal and we project onto C3 times C3, we remain onto the diagonal. So this is what makes the composition to be the projection onto the intersection. Okay, so how does it look like Douglas-Rachford if we apply it into the new reformulation? So now we need to consider K and B with the notation in the reformulation. Now we live in the space H R minus 1. So we consider R minus 1 initial points. And then for the iteration, this PK here is the resolvent of K. It's not only the projection onto the diagonal, but its composition with the resolvent of the last operator. Then the parallelization is only in R minus 1 components, but the iteration looks exactly the same. And the conclusion is the same. The sequence PK here, which is the shadow sequence, converges quickly to a solution of the monotone inclusion. So for feasibility problem, if we do the same in the same instance, now we only need to consider 2 initial points. And in order to build PK, P0, we compute the average and we project onto the third set. This is P0. And now from here, we get into the parallelization. So reflection, reflection, and middle point. And the same for X2. Okay, reflection, reflection, middle point. And from here, we restart the iteration. Middle point, projection onto C3. And so on, we generate the sequence PK, which is again weakly convergent to a point in intersection in this case. Okay, so I said that for the convergence, we needed convex sets in the case of Douglas-Rachford. But the case is that it has also been employed in non-convex setting. For example, for reconstruction of proteins, Sudokus, and other puzzles. I will recover Sudokus later. However, the theory is much more limited, and we have a few results warranting the convergence in non-convex scenarios, like the sphere and the line, or the half space and a non-convex set. The case, what we concern here is that in applications, usually the problem is defined by more than two operators. So we need the product space reformulation to work for non-convex feasibility problems. And this is the case in both reformulations. So for example, if we consider C3, we replace it by this non-convex set with the elements 1, 2, and 3. In this case, the intersection is only the point 2. So we can replace everything in the reformulations. So C3 replace it by its set. And everything works exactly the same. The intersection of the two new sets is equivalent to the intersection in the original space. We can compute projectors component-wise. The diagonal is still convex, so it's the same set. In a new reformulation, everything works the same, but we need to take care with one observation here. C3 is the grid of the 9 points. C3 times C3. The set K, where we want to project, is its intersection with the diagonal, so only the blue points. If we want to project onto the set K, we might do the same as before. First, we project onto the diagonal and project onto C3 times C3. In this case, both projectors are single values, so we have no problem here. But we might have, in this scenario, this particular instance. If we want to project this point onto the set K, we first project onto the diagonal. And now, from here, we have 4 different projections onto the set C3 times C3. So in order to make this a projection onto the set K, we need to be sure that we keep only those projections which remain on the diagonal. Okay, so we will avoid these 2 projectors, and we will only consider these 2 possibilities. Then these 2 possibilities are actually the 2 possible projections onto the set K. Okay, so we will compare both formulations in 2 different problems. First one is the generalized Heron problem. The original problem is the problem in the plane. In the plane, we have a line and we have 2 points. And we want to find the point in the line that minimizes the sum of the distances to the 2 given points. So for example, this could be a solution. The generalized version replaces the line by a convex set and the points by convex sets too. Okay, so we want to find the point in the ball that minimizes the sum of the distances to the squares. And now we don't have only 2 points that are squares now, but we have an arbitrary number of squares here, r minus 1. And we don't need to live on the plane. We can live on any Euclidean space. Okay, so we can control here the number of constraint sets and the dimension of the space. This problem can be equivalently solved by the monotone inclusion of finding a zero in the sum of the subdifferentials of the sets plus the subdifferential of the indicator function of the feasible set, which is the normal cone. So this is a monotone inclusion defined by R operators. Okay, 1 for the ball and R minus 1 for the squares. And this is a problem that was proposed and solved by Mordukovic, Nam, and Salinas in this couple of papers with modern convex analysis tools. In fact, they implemented a Douglas-Rachford type algorithm for solving it. So in here, we consider instances, randomly generated instances, as in the picture. So the set in the feasible set, omega r, would be a ball in the space, and the other ones could be hypercubes, so squares, cubes, or hypercubes in higher dimensions. And we will compare the performance of the standard DR and the reduced DR, where I will call standard DR to the Douglas-Rachford with the classical product space reformulation with R fold lifting, and reduce DR to the new one that we have proposed. First thing is computing some kind of numerical experiments in order to choose or to tune the parameters of the algorithms, but I won't show these results. I will go directly to the comparison. So the first experiment, we fix the number of operators to 5. So we have the ball and 4 squares, but we will move the dimension of the space. And I'm gonna plot the time ratio between the standard DR over the reduced DR. So for example, this is the first instance. If I got a ratio of almost 4, that means that reduced DR was almost 4 times faster than the standard version. So points above the line will be where reduced DR is faster. Points in here, standard DR is faster. So this is for N100. So I repeat for the same size, I repeat for several generated problems and several initialization. And then I repeat by moving the size, the dimension. So the first thing that I note is that all the instances are actually above the line. So for every instance, reduced DR was faster, or at least not slower, because we have something close to 1 here, at least not slower than the standard DR. And if we compute the average, or I think this is the least square regression line, we can say that on average, for all sizes, on average, reduced DR was almost 3 or a bit more than 3 times faster than standard DR. Now in the second experiment, I do the opposite. I fix the dimension of the space, and I'm gonna increase the number of operators in the monotone inclusion. And then I get these results. In this case, I do get points below the line 1. So there are a few instances where standard DR was a bit faster than the reduced. And the trend now is decreasing. So that means that when the number of operators in the monotone inclusion increases, then the advantage of reducing the dimension of the product space is not so clear. It's not so favorable to the algorithm. But in any case, when the number of operators is really large, none of the implementation will be efficient for the numerical point of view. We need to store many sequences at the same time. And finally, the third experiment is the same setting as the first one, but only with 3 operators. And these are the results. So why do I repeat the first experiment with 3 operators? Because now we can incorporate the RIU algorithm into the comparison. RIU algorithm, when we were discussing about minimal lifting, in the case of 3 operators, RIU showed that the minimal lifting was twofold by providing a new splitting algorithm. So I'm going to include this splitting algorithm into the comparison, and I get these results. The red one is for RIU. So reduced DR and RIU were around 4 times faster than the standard approach, but it is true that RIU was a bit slightly faster than the reduced algorithm that we proposed. Okay, and finally, in order to test the reformulation for non-convex feasibility problems, I I took Sudokus again. Sudoku is a puzzle where we want to fill a grid, a 9 times 9 grid, with the digits from 1 to 9. We have like 4 constraints. Some of the cells are already filled. In each row, then digits from 1 to 9 needs to appear only once. The same for the column and the same for the subgrids. So in order to find a solution to the Sudoku, we can define a feasibility problem with 4 constraints. First one is the sets containing all the matrices that complete the given one. So all the matrices whose given components take the values that we were told. C2 is the matrices whose rows are permutation of the numbers from 1 to 9. But we don't care about the columns. We only care about the rows in here. C3 is the same with the columns. And C4 is the same with the subgrids. So Sudokus live on the intersection of these 4 sets. So this is a feasibility problem that models the Sudokus. However, this formulation of the feasibility problem is like really bad for Douglas-Rachford. Douglas-Rachford fails to solve the problem. But we have a reformulation as a 3-dimensional multi-array with indicator variables. So now we have like 3 indices. I and J will be the position in the Sudoku, and K will be the digit. And we assign a 1 if the digit K is assigned in this position, or a 0 otherwise. So the reformulation looks like this. Okay, we have 3-dimensional array. In the bottom, we have the Sudoku. And if we want to put 6 in this position, then we put actually a vector with all the components 0, but the 6th component, which will be the 1. So everything can be reformulated in terms of this reformulation. The constraint set will look like something like this. And I won't get into the details of the formulation and the implementation of projections, but just to say that these sets are defined in terms of saying that each part of the array is a vector of the unit basis, of the standard canonical basis. So the only thing we need to know is how to project, just to mention before that, this is the formulation with indicator variables is actually by Elser and Ragenburg and Thibault in this paper from 2007. But I will take the reformulation with the 4 or 5 constraints that they made Fran Aragon with John Borwin and Matan. And as I say, the only thing we need to know is how to compute projections onto the canonical basis. And this can always be done. If this is the point that we want to project, we just take the maximum of the components and we pick the element with the 1 in that position of the maximum. Okay, if someone is interested in the details of the implementation, you can look further in the papers. Again, we are going to compare standard DR and reduced DR for the Sudokus. I will consider 95 Sudokus with 10 initializations each. And since this is non-convex, we have no guarantees for the convergence of the algorithm. So I will label as an unsolved instance after 5 minutes of the running time of the algorithm. So this is the statistics of the comparison. Both algorithms solve around the 90% of the algorithm, the instances. But in terms of wins and the average time required to solve each Sudoku, reduced DR is clearly the winner. Okay. If we want to plot these results, I'm going to do this. I'm going to plot the percentage of solved instances against the CPU time of both algorithms. And it is true that we can see nothing in here because the main part of the instances were solved at the first seconds. So I'm going to make zoom here. Again, two lines are really overlapping, because we can see that the competition is actually on the first seconds of the running time. So I'm going to make zoom again. And here we can see that reduced DR was consistently faster than the standard DR. Okay, so for the same CPU times, it solved more percentage of instances of the Sudokus than the standard approach. And pretty much that's all I wanted to say. I have only included the main reference here because I have been showing the references along the talk. You can look for the references in here. Otherwise, you can contact me. That's all. So thank you very much for your attention.
Thank you, Rubén, for very interesting talk. Now it's time for questions.
Hi, Rubén. It's good to see you again.
Hi.
It's been at least 3 years since you visited us. Okay, thank you very much for your interesting presentation. I apologize, I was late for your talk and I missed the beginning. I'm really sorry for that. But I was right on time for you to mention 2 of my papers from 40 years ago.
Actually, I'm not really sure if those are the papers that you sent me, because you sent the original PDF file in Russian. So I couldn't even identify the title. I think these are the papers, but
I'm not sure either, because I have not so good memory to remember what was in what paper from 40 years ago. But I want, first, everything can be checked. If you really need references, of course, I can check and tell you. Just a small comment. What you call a new product space reformulation is likely, very likely, to be the same age as what you call the standard one. That is at least 40 years old. But I can't prove it immediately. It is just my observation using my very outdated memory. But it can also be checked if you need it. Okay, thank you again. Keep producing good work and keep presenting at our seminars.
Okay, thank you.
But tell me if you need any references or whatever.
Yeah, just a question. What do you mean just now that the new product space formulation is only 40 years ago?
I think, at least if you refer to my papers, I used both reformulations, what you call standard and what you call new. I suspect that all these things were in those papers. Can't remember exactly what is in which paper. I might be wrong. This is just from my memory.
I will
at least I'm familiar with both.
Okay, thank you.
Oh, good. Marco is here. Oh, good to see you, Marco. Sorry, I'm turning off my microphone. Hua, back to you.
Okay, so anyway, if you send Rubén reference, you have to translate into English as well.
I think Rubén is already good at reading Russian, aren't you?
I only understand the math part of that paper, the numbers.
And this is all you need?
Yeah.
Okay, so we still have time for other questions. So everyone just move yourself and then ask Rubén questions.
Rubén, Gary Newsom here. Thanks for the talk. Just wondering if you, in your experience, do you now have any guidelines as to what's the best choice for the one of the constraints to include in the diagonal? Is there some sort of, should you include the biggest constraint or the smallest constraint?
Yeah, actually, I don't have like much experience because I only computed like these 2 numerical experiments. But I don't know in the case of convexity, once you have everything is convex and so on, I don't know. But in the case of Sudokus, it is true that all the constraints are non-convex, but one. One of the sets is convex. It's actually a subspace. So this is the one that I merged with the diagonal. It is true that I tried the other possibilities and the algorithm failed to find the solution. So I think you need to keep something to make still the new diagonal to be at least convex.
Thanks.
You're welcome. Thanks for your question.
Okay, we have a question from Hans.
Very nice talk, Rubén. Thank you so much. And thank you, Alex, for your comments. I would love to get a reference for the reduced formulation. Alex, if you have one, please send it to me as well. It's really awesome to get the history right. So Rubén, I have one question about experiment 2. When you increased R, it looked like the classical dr started to become better and better. So if you keep cranking up R, will the classical formulation win or not?
I think when I increase like more and more and more, then all the points would be around the line 1. So maybe the difference between one formulation or the other is just a few iterations or a few milliseconds.
Okay.
So actually, it is not that one of them is clearly better than the other. It's like both require like a lot of iterations and there's no clear comparison. So I don't know.
Okay, thank you. And maybe one more question, if I may. Of course, there's this algorithm by Malitsky and Tam, and we have Matt here in the audience, which is awesome. So have you compared your performance to their algorithm yet? I mean, you have the Rio comparison for 3, right? But you might want to compare it also to Malitsky Tam.
No, I didn't. Just the 2 papers like were submitted to archive with a difference of a few days. So I didn't do it in the original submission and I didn't have time yet to, but this is something I want to do. Yeah.
Cool. Yeah, and I have one last comment. I've been working on with Shambhavi Singh and Sean Wang on studying this for normal cones. So for normal cones, you actually get strong convergence for Malitsky Tam, for Rio, and also for your algorithm. So and you can use it to compute the best approximation on the intersection. So it's an awesome algorithm. Thank you very much, Rubén and Matt, for giving us so beautiful algorithms. Thank you.
Thank you.
Okay, we still have 2 minutes, so one quick questions from everyone. Otherwise, we will close the seminar here.
Okay. Maybe I have one quick question, if it's okay, Paul?
Yeah.
Okay. Yeah. Thanks for your talk, Rubén. And yeah, I really appreciate all the pictures. I know that it takes a lot of time to prepare those, but really, really helps. So really great. I just have one question about, so with this reduced formulation, you push one of the operators out of the product into the normal cone part. And I can see sort of how that works, but I'm just wondering, is there any possibility to do some other kind of trick that is not exactly what you've done there? Or is this kind of like just the only possible way that you could try and do something like that?
No, I don't think it's the only possible way.
Okay.
It's the way that made it, everything works in the proofs. The case is that I did it originally for the case of feasibility problems. And in this case, I think this is the only possibility because you lose the parameter in the result.
Right.
When I try to generalize to the maximally monotone operators, then I needed to rescale and to include some parameters. Sorry, it's my phone. I needed to rescale it with the factor by r-1 in order to make everything consistent. But maybe there are other possibilities to make the formula to be true. I don't know. I think for the case of feasibility, maybe it's the only possibility, but when we try to generalize, there might be others.
Okay, thanks.
Yes. I also have only one small comment. First, thank you, Rubén, for some very nice talk and very nice formulation. Actually, for the feasibility problem, Matt and I and other two other co-authors also try to have another reduction formulation for the feasibility problem. I think you might aware of that, but of course our formulation is a bit different because we require some additional assumption. But we also reduce to R minus N.
Yeah, it is already considered in the paper. So I mentioned your reduction technique. Actually, one of the proof of my paper is based on one of yours. So basically, the idea is the same, but this is something that works without any assumption.
Okay.
So I think that's the difference. So maybe it could be possible even to combine both approaches. When you have the assumption, you can reduce with your formulation and then reduce again with the tree.
Okay.
So maybe you can even remove two constraints from your program.
Okay, thank you. Yeah.
Thank you.
Okay, so thank you everyone for your time. So I think time is we have to close the seminar here. Thank you everyone for coming. So have a good week ahead. Thank you, Rubén. I'll keep coming to Australia.
Thank you, Rubén. Nice talk.
Thank you.